Hello, my name is Miss Milberg. Hopefully you read my introduction from Mr. Belter the week before Thanksgiving was when he posted it in Google Classroom. If you didn't, or if you are just remembering now that you've got me this week, that's why I'm here. I am doing a short field experience, so student teaching, but a short version. So I'll be with you for the week, and I am really excited to kick off a new unit. We're going to talk about kinetics, chemical kinetics. I've got our learning objectives for today's lesson written on our first slide, so let's take a moment to read through those. By the end of today's lesson, you should be able to say, I can explain how and why different factors will affect kinetics of a reaction, and I can express the rate of a reaction in terms of reactant and product concentrations. So, before we get into the meat of it, let's do a quick warm-up because it's been a while. Let's get our brains back up, turned on for school. So, how do we calculate velocity? It's a pretty simple question, but why it's important will be very clear on the very next slide. How do we calculate velocity? Hopefully, your answer is something very much like this. V equals delta x, you might have written delta d over delta t. So V equals the change in x or the change in d. Usually if you write change in x, we're talking about displacement more generally, rather than distance, because we usually think of d as distance. And then delta t meaning change over time, or change in time, pardon. And why is that relevant? Well, when we're talking about chemical kinetics, we're talking about the rate at which reactants are converted into products. And when we're talking about that, we use a formula that looks an awful lot like our distance formula. But I brought this little graph up, and it is of a fictional decomposition of substance A into substance B. So if you look at the yellow line, that represents the concentration, as it says over here on the left, over time of reactant A, and then therefore the appearance of product B. And as I said before, that velocity formula was important because we talk about the change in position, or the displacement over time. Well, here we're talking about the change in concentration of A over time. Please do notice that there is a little negative sign out in front in here. Why might that be, do you think? Well, of course, it's because as A is being used up, as A is disappearing, B is appearing. So B is going to have a positive rate of appearance, but A is going to have a negative rate because it's disappearing, it's going away. So if we want to write that out in more explicit terms, we look at the concentration at position, or at, for example, if this were time t for A, we would say that this is time t, this could be our t1, and then this would be our concentration of A sub 2 and our concentration of A sub 1. And then if we want to write it in shorter notation, we use our delta again, which is, of course, change in. I want to make a note about the brackets. So when we use brackets around, here I've used it just around the letter A, but if we're using it around a substance or a chemical formula for a substance, it's going to represent concentration in moles per liter. And of course, it is important to think about our dimensional analysis, about our units. The units for rate is going to be moles per liter times seconds, which makes sense if we look up at our formula. We've got moles per liter because we've got the concentration in brackets, and then we know the time is in seconds. When we talk about rate, we can talk about average or instantaneous, again, just like velocity. And an average rate is going to be the change over a longer period of time. Whereas if we're talking about an instantaneous rate, we're talking about a line that is tangent to the curve. So actually what I've shown you, I apologize, my lines, I just realized, are on the rate of appearance of the product. These are not the rate of disappearance of our reactant. This is the average rate of appearance of product B and the instantaneous rate of product B. But instantaneous especially is going to be an important rate that we are going to use in the upcoming days, because especially if we use the instantaneous starting rate, so if we looked down here and if we had, pardon me, again, not on the B line, if we're looking at the disappearance of reactants, if we had a tangent line right here at the very beginning, that is when, for all intents and purposes, we assume that there is no product and everything is purely reactant. And so that is a value that we're going to be paying attention to, especially in the upcoming days. We can talk about our our concentrations in terms of the reactants and the products. As I said before, reactants disappear and products appear, so it's important to pay attention to our sign conventions. And in order to relate product and reactant concentrations, we need to use the coefficients of a balanced equation. So let's look at this. If we've got this nitric oxide reacting with oxygen gas to form dinitrogen oxide, we are going to be able to relate those together by using their coefficients. Basically, by thinking about how much reactants are used up per product that is formed. So for every two, and we want to think about this obviously in individual units. So if we were to divide that by 2, sorry, I'm getting ahead of myself. Let's look at this and then we'll talk through it. So again, our rate here is negative because for every nitrogen oxide that's used up, it's going to go away. It's not going to be there anymore, which is why we have a negative sign there. Oftentimes, it is good to define all of your reactants and products in terms of one specific one, and it can be very useful to look for a product or reactant that does not have a coefficient. So in this example, this is why I've gotten ahead of myself, and I do apologize, but in this example, we're looking at oxygen. So oxygen, for every 1 oxygen that's used up, that means we've got 2. So we're going to get half of our dinitride trioxide that is formed, which is why over here it's a positive, but we're still dividing that concentration by 2 times time. And over here, our nitrogen, we're using up a quarter of that. And we can use this information to talk about if we know, for example, if we know an instantaneous rate of one of our either reactants or products, we can determine the rate of appearance or disappearance of the other reactants and products. So for example, using this equation, how fast is our concentration of oxygen decreasing when the concentration of nitrogen oxide is decreasing at a rate equal to 1.6 times 10 to the negative 4th moles per liter times second. So here, we know how fast this is decreasing, but this is as a single mole. So when one of these is disappearing, how many oxygen will also be disappearing? Well, in our balanced equation, we have 4. So we'd have to divide essentially the coefficients of all of these by 4. And it's going to look something like this. To set that up, we would write our rate and set that equal to, pardon my little bar there. Our rate is equal to the disappearance of the concentration, or the disappearance of the concentration of nitrogen oxide, which is equal to 1/4 of the disappearance of diatomic oxygen. Then we can shuffle our numbers and everything around, and we can find out that the disappearance of oxygen will be 4.0 times 10 to the negative fifth moles per liters times seconds. So with this information, you should be able to work through a couple practice problems. If you have any questions, you need some clarification, you want to go through this, please feel free to send me an email. And I look forward to seeing in quotations you throughout the week.